Hello everyone. Today we are here for Lab 5 Magnetic Braking with Faraday. The purpose of this lab is to observe Faraday's law with the help of interaction between magnet falling through an aluminum tube. Faraday's law states that when a magnetic field changes in strength or orientation in a closed loop of wire, an amp is induced. Lenz's law states that the direction of an induced current in a conductor will always oppose the change in the magnetic field. Then the gravitational law states that F is equal to mg. And then there is Ohm's law, which is required for the experimental observations. So this is the experiment. We'll just drop a tiny magnet, drop a half meter long rod, and the orientation does not really matter because the M generated will always be opposite to the force it is the magnetic moment, and so that is why the time would be the exact same. There is no air resistance. That is our assumption. This is the result. Upon three observations, we get 10.9 seconds. The length is 0.5 meters, magnetic moment 2.2 ampere meter squared, and the mass is 30 grams. So what happens due to Faraday's law, there's an induced amp which opposes the motion of the magnet, which reduces its speed to a terminal constant speed. If the magnet was falling in a free space, uh, it would not experience the same force, and so it will fall down like just any other object. This is the experimental model. You can pause to see it. So this is what we get. So after like around zero point 0.5 seconds, it gets to its terminal velocity and it stays there. And then as soon as it leaves the 10.9 second, it just goes down, which basically means as soon as it leaves the tube, the forces of the amp is not really taking a part in the velocity, in changing the velocity. The checkpoint, why can't we use a Ferris wheel? Because it has magnetic properties of its own and it would mess up with the calculations. So this is the experimental and computational values. So the computation is 10.5 seconds. The simulation basically states that it asks what color is clockwise and what color is anti-clockwise. The red is counterclockwise and the blue is clockwise. This is because in the first case, the magnetic field points down as the north is facing downward and vice versa. What happens to the dynamics of the system when you flip the magnet around does not really change anything. How does the total time in tube it changes? I think the inaccuracies were due to the inaccuracies of stopwatch, human intervention, influence of air resistance, and other magnetic fields. This is the velocity versus time graph. So you can see it teaches its terminal velocity. The assumptions, computational model are none. The experimental model, we ignore the air resistance, other magnetic fields, human error in measurement, and the magnet might not have been perfectly perpendicular to the surface. What if the resistivity was reduced to around zero? The current generated would be much higher. What if there were holes? The amp would be less because there would be disruptions in the electromotive force, so the induced current would be less. Thank you and have